Okay guys, so we'll start with the second session. I know some of you have already started working on the lab 2, but I would like to cover the theory part of it as well, and you can continue working on lab 2. So this session is about data management, and what we are going to cover here is CPU and GPU memory. Why did we didn't have to do this memory copies the previous session? We are going to see how to now do it manually, and then the last session is basically on optimization, right? So as we had told last time, CPU and GPU basically are two different architectures. Both of them have different kinds of memory. One is a high capacity memory, another is a high bandwidth memory. GPU memory is lesser, but it is very, very high bandwidth. We have seen in Volta, we have around 900 gigabytes per second. And if you can see in this diagram, your CPU and GPU memory are connected to each other via something called as I/O bus. Now, different kinds of I/O input-output bus are present. Like in a typical x86 based architecture, it is the PCI Express bus, which gives you around 32 Gbps speed at this time, right? If it is a power CPU architecture, you have a new kind of a interconnect which is called as NVLink, which provides you higher bandwidth and lower latency. So based on which CPU architecture it is, the CPU and GPU are connected to each other via a I/O bus, right? And it needs to get transferred. In the previous section, we actually used something called as CUDA Unified Memory. As we are right now at CUDA 10 version, we have gone through 10 different cycles of CUDA releases. We are currently at CUDA 10, and with every release, we make it much more simpler for the user to make use of GPUs. One of the features which got added in not just in CUDA 10 but the previous version as well was CUDA Unified Memory. Now what is this unified memory? So you can see on the left hand side you have something called as without managed memory, where you can clearly see that the memory that is there on CPU you usually allocate using malloc or new, and it gets allocated on your CPU. The one that you allocate on the GPU will remain on the GPU, and they have to get transferred, and they are two separate memory. I can't pass a pointer which is allocated in CPU memory to GPU because those address spaces are completely different. While in unified memory, or also called as managed memory, the user or the developer doesn't need to worry about this. For him, CPU and GPU memory is one unified memory, and you don't need to explicitly transfer the data. Behind the scenes, this transfer happens. It happens via page migration engines. The driver actually takes care of transferring the data wherever it is required. If you are accessing that data on the CPU, it transfers the data to the CPU. If it is required on the GPU, it may transfer it to the GPU, right? So it is hidden from you, the driver. There was a question on what changes we have done to the operating system. This is one of the changes we have done, where we actually modified the page migration engine, where we actually take care of transferring the pages based on where they are required, so that it is hidden from the user. Now, that is what you saw in your previous case. If you did, remember, you said -TA equal to Tesla : managed. Now, this managed is not an OpenACC feature, by the way. It's very specific to the hardware. That's why it is after colon, right? OpenACC states that it's -TA equal to something. It does not state what comes after colon. After colon is more of a specific to a compiler. PGI supports this feature called as unified memory :manage, which knows that CUDA basically supports this unified memory concept, and let me start making use of it. While GCC does not support unified memory. So OpenACC implementation of GCC will not understand :managed. It will be only understood by PGI at this point of time. Over time, GCC might also implement it. The reason I am telling you this is, as soon as you added :memory, you actually made it reliable on a compiler, not on the standard, correct? So you said that I want to make use of this feature which is by PGI, which adds this managed memory concept, so that NVIDIA CUDA unified memory comes into the picture. What if you don't want to depend, you want to be truly portable? In that case, you will remove that :manage so that it can run even with GCC or Cray compiler or any other compiler which supports OpenACC, right? That's one of the reasons why you might not use managed memory. Second one is, whenever you use unified memory, it's just too late, which means whenever I need it, whenever I touch it on the GPU, it gets transferred. So it is runtime, correct? You can actually control the behavior of this data transfer by explicitly copying them in advance, which can improve the performance of your code, right? This is something which is only possible when you explicitly do these data transfers manually, okay? And that is what we are going to learn in this particular session, which is basic data management, right? So as I said, there is always a host, which is traditionally a CPU. There is a device, which is generally accelerator like GPU. And if you are not using concepts like unified memory, you have to explicitly manage the transfers between GPU and CPU, right? So it's the same thing again. We need to do this transfer. So suppose now in your code, you were always using -ta equal to Tesla : manage. Let me remove that colon manage. As soon as you remove colon manage, you will start getting error in your code. It won't even compile. It will start throwing errors like size of the GPU is unknown. Why? Because if you see, compiler does not understand here how much data to transfer. Only the programmer knows, right? Why do you, in a malloc or new state, how much memory you want to allocate? Because you know how much data you want, right? Compiler does not know that. Similarly here, it is actually throwing an error telling you that this, I don't know how much data to copy, so I can't even compile your code as soon as you remove this colon managed part, okay? So what do you do about it? You start making use of data copies, right? Managed. So this is the second clause that we saw. So there are different kinds of clauses which are there. The first clause is copy. Copy means that I need to copy whatever is there inside an array to the GPU, and once it is done, I need to copy out the data as well. So it's an input which gets modified inside your loop and then copied back to the CPU, okay? Copy in is just, it's an input. So you just create and copy in the GPU. You will never take it out. What kind of a variables you don't take it out? Which are input variables. They don't get modified at all. So you are just copying into the GPU, and copy out is basically only for allocating on the GPU and copying out the data. What kind of a variables are there? Output variables, which you are modifying. Like if you remember the previous example, in the first calc nest, A is your input and A new was your output. In the swap function, A new was your input and A was output. So similarly like that, you will choose what is input and what is output, and create basically just allocates the memory, and it will never copy in or copy out. Any guesses of what create will be used for? Sorry? Temporary variables in between, right? You don't need to copy in, you just use it and then discard it. Those kinds of variables will be put inside your create, right? So array shaping is basically telling how much data to copy in, out, or copy, right? So you can see an example here. This is the C++ syntax and this is the Fortran syntax. In the C++ syntax, you will give the name of the array and then you will put the start index colon the length. What is generally the start index in C? 0, right? And in Fortran, if you see, it's the starting index, which is generally 1 in Fortran, and then the ending index. It's not the length. It is the ending index. It's not the length. So this is the difference between C++ and Fortran. I'm not sure if anybody is a Fortran programmer here, but you will put the starting index and the length. If you are copying suppose 8 elements, you will say 0 colon 8. Here it will be 1 colon 9 basically, right? So, and you can also do it for multi-dimensional arrays. That was single dimensional array. Similarly, you can do it in multi-dimension. This is a 2-dimension array. You are saying I am copying from 0 to 1 in one dimension, 0 to m in the second dimension. So you can copy multi-dimensional array as well. Or you can also copy partial arrays. You don't need to always copy the full array. Based on your input and output, you can only copy partial arrays. Like in this particular case, I am only copying from this starting and I am only copying n by 4 number of elements. So it depends on what your application is and how much data you want to transfer in and out. So in your code, you are now going to modify, you are going to start the lab 2, and what you are going to do is basically, as soon as you remove manage clause, it will start error And then after that error, you are going to start doing copy in, copy in, and copy out like this. I already told you a new is copy in only, right? And this is copy out. You don't need otherwise, right? But to be on the safer side, if you want, you can just use copy. This is something that you are going to add in the lab 2. And if you can see now, the code will start telling you more information. It is telling you generated copy, right? So it will tell you this, whether it is explicit or implicit, it will also tell you that, right? Generating copy in at line number 62 for copy in for this one, copy out for this one. This is very, very important to note in the second session. Yeah. Okay, so the question is, what is different between implicit and explicit? Is that the question? So, as a name, as a grammar itself tells, as in what it means. So, explicit is that you have explicitly told it to copy. You have told it here, I need to copy. But implicit is that compiler sometimes itself can understand there is a copy required. So, it will generate an implicit copy. That's the difference between implicit and explicit copy. Got it? Okay. So like, just to give you an example, it is telling implicit copy of error because it is required outside, and if you can see, you have never told error here. So it has implicitly generated a error output, even though, because it's just a single element, it was also able to detect what was the shape of it, right? So as soon as you start running on the GPU, this code, instead of seeing a performance improvement, you will actually see a slowdown. Okay, so you can see your previous number was 41. As soon as you add those data clauses, it will actually give you a slowdown. So don't worry, there is a reason for it which we'll explain. So now the code will run, it will give you the right output, but it will become slower, right? What is the reason? Again, as I told you, don't start guessing anything. You can actually use the profiler. For here, since it's a simple code, we are showing the snapshot of the code. This is an example of the profiler. As you can see, what is happening every time is, if you see, this is a snapshot. This is called as a timeline view of the profiler. When I say timeline view, what it is showing is across time from left to right, where was my time spent, okay? And you can see here that it is basically showing that this is my function called as calcnest, this is calcnet function, this is swap function, this is another function which I have made parallel. But apart from that, you see these two things, which is memory copy, okay? It shows memory copy H to D and D to H. What is H to D? Any guesses? Host to device and device to host. So now it should be visible to you. Where is your time spent? It is not in the compute. Where is the time spent? On the data transfers, right? Your profiler, it will be much more evident when you profile it. So most of your time will be spent in your data transfer rather than the compute part of it. So why does this happen? Because if you see, this is the outer while loop, correct? At every while loop, you are telling copy in, copy out, copy in, copy out. Keep on doing this again and again, again and again, again and again, till the time this while loop finishes, right? In managed memory, this was not happening because once it got into the GPU, it was always on GPU, correct? You were always running on GPU, it never came back to CPU, so it never had to do these transfers again and again. But here, you have told it that I want to transfer this data explicitly. So every time you do this, you are doing this transfer. Is it needed? Not needed, right? So we have to work and do something about it, for which we are going to optimize the data movement, for which we'll use more clauses of data. So the first clause that you need to look at is called as the data clause. So like your pragma clause, this data clause has a scope, right? So I can say within this scope, as pragma ACC data, and then here the clauses will be what? Copy, copy in, copy out, whatever I told you. So whatever I say here, it will happen at the start. So suppose I say copy in, what will it do? It will create and copy the data to the GPU. If I say copy out, it will create and output the data at the end, correct? So within the scope is what it will remain. It will not do any of those transfers inside again and again. Got it? So that's what is the main thing about the data clauses. Let's see an example here. Hash pragma ACC data, copy in, right? So in the beginning you have this data A, B and C here, correct? In your host memory, which is your CPU memory. Now I have said copy in and copy out. So what happens when I say copy in? First, a device memory gets created for A, okay? For A, because it is here at this point of time. Then copy A from CPU to the device. It got copied to the device from here to here. After that, it went here. So B got allocated and it gets copied to the GPU from host memory to the device memory. Then I say copy out. Copy out will just allocate. Will it copy inside the GPU the copy of C? No, because it's just an output, correct? Once it has reached the end, it will basically then copy the output. When it has reached the end, it will copy from GPU to the CPU, which is device to host transfer, right? So that's how your data clause actually works. So the scope is from here to here, right? And then finally it will deallocate all of them as well. As a good programmer, you should also deallocate memory and not forget about it. So it will also deallocate the memory on the GPU, right? So this is the step which gets followed. So for you, what you are supposed to do is, if you have a while loop like this, I can add a data clause within this scope outside, okay? So that there is no transfers which keeps on happening again and again. Please note that you are still mentioning copy in and copy out here. That has not gone away. It will still be written because the compiler needs to know the size for compilation. But the copy will only happen where? At here, this location, outside. Okay? So then you can check it here basically that at line number 60 here, it would have generated a copy and copy in clause at that particular line number. And as soon as you do that, ideally you should get better speed up. You should get better speed up because now you have taken control of transfer and you should be getting better performance as compared to unified memory. The newer architecture and newer CUDA version, generally the speed up will not be too much because unified memory has reached a stage where it will give you almost the same performance as data copy. But this is for your reference that you can see there will be some improvement which you will get if you start using data memory, right? So what have we learned so far? We said that unified memory is something which is managed by the driver. If you want to take control of it, it's a very powerful tool when you start porting the code. But once you know that you have reached the performance, you can start taking control of it, which can be done by this data clauses. Moving data at each loop is not at all efficient. You need to manage the data very, very efficiently. Now there are some cases where you might need the data in between that clauses. For that we have something called as update directives as well, which you might not use in this particular session lab which you are doing, but it is something worth noting that if I use something called as hash pragma ACC update device in between those data clauses, it can update your device as well. Somewhere in between, if you feel that you need a data that needs to be transferred, you can say hash pragma ACC update device and it will get updated on the device. If you were updating host, then you can say hash pragma ACC update self and it will update from GPU memory to the CPU memory. This is something which usually happens especially when you are using MPI based programs, because MPI you will do something on the GPU, in between you will need communication. So before the communication you will say update, right? So that because MPI call is basically a CPU call, right? In that case, you will say update and it will get copied there, right? And this is another very important thing. Till now, we were assuming so far that your code is within one function. Do you see this? But have you noticed your code? Is it like this? Is it like this? You have two functions, actually three functions. This while loop is in main and this is somewhere else. So can I just put a bracket like this? Not possible, right? because this is a structured region. Structured region is that everything is within one function and I can just put this braces before and after. What about C++ structures, classes, or the example that you have? In that case, you need something called as unstructured data directives, which is very similar to the structured but with some additional thing. So you have something called as enter data and exit data. So enter data and then clauses. So wherever you want to start that data section, you will say enter data and write the right copy, copy in, copy out, whatever is required. Wherever you are done with it, you will say exit data. Got it? Right? So to give you an example, I have more and more example of it. There are various clauses, as I already told. This is one example which is very similar to the code that you have. Now here is where I am allocating the memory, so I am saying just create. Whenever I am deallocating, I am saying delete, right? And then here is my kernel basically, right? So it's in different function altogether. So I can say enter data and exit data at different function levels, correct? So another example, the basic example which you will usually see is in C++. So generally in a C++ world, where does the allocation happen? Constructors. Where does the deallocation happen? Destructors. So you will say enter data, copy in and create inside the constructor, and you will say exit data and delete inside the destructor, right? So what you are going to see and do in this particular lab is basically to make use of this unstructured data region and remove that managed memory and try to make your code and try to see if you get more performance, right? So we saw difference between CPU, GPU, unified memory in the beginning. We have now seen array shaping, data clauses, structured data region, update clauses, unstructured, and in the next lecture we are going to look at loop optimization. So without ado, you can go back and start the lab again, which was there, and directly go to the lab 2 and start working on it and get the results out of it the way you did it for the first lab. And again, it will be a 1 hour timer which will do as soon as you say start activity.